here, pre-calc style. Today we're going to be covering logistic growth, which is I think fairly new all around to you. You don't even have much prior pre-calc experience. In fact, any prior experience you might have might be actually from like science class or something, right? Have you done models that look like this before? Okay, so this is all in the name of a slightly more, perhaps realistic population model. Obviously, populations grow exponentially, maybe for a time, but it's not necessarily a tenable assumption to assume that they'll grow that way forever. So yesterday, just to recall, we've already discussed this differential equation with this as its solution. And remember, we got that differential equation by making this statement and translating it into the math, the one I have in bold italics here. Yes? So it all kind of, again, we want to kind of make sure at every stage we have something that makes sense. But today we want to add another assumption. We like this assumption, but we also want to have it be proportional to something else too. And that's something called the carrying capacity. I think, like I said, even in a science environment, I think you've maybe talked about this, right? And in fact, bacterial growth looks very much like that. If you see bacterial growth often has this nice exponential phase or the growth phase. There's this lag phase at the beginning where they're where maturation is being achieved, and then they launch once they all mature, and then they based on whatever the media is, they actually die out pretty quickly. It actually doesn't look quite as logistic as we might like for today's example, but that's kind of a bacterial growth curve. And then, once the media has been used up, there's some resource in your environment that limits your growth, right? For bacteria, it might be the media that they put in. For humans, it might be geography or resources of some kind, food. So I'll give you a chance to read my paragraph if you haven't already. So here's the logistic differential equation. And see if the thing I underlined in words matches what this says here in the equation. We have the rate of change of the population is both proportional to the population, current size, right? That obviously affects the rate of change. We want dp dt to go up, don't we? If p does, right? So that's what's happening here. That makes that happen. But we also want it to go down if we get close to the carrying capacity, right? So if we call the carrying capacity m, then I think the way you would calculate the remaining bit, the remaining fraction of the carrying capacity that we have left, we would calculate that as just as a simple fraction, right? How much is left? Our current population is p. If the carrying capacity is m, we don't want it to go above that, then m minus p is the amount left to grow, and m is the total carrying capacity. So this represents a fraction of the carrying capacity that remains. So now we have that dp dt is proportional to both. So as we get close to the carrying capacity, what happens as we plug in p-values that are, if we have a population that gets very, very close to m, then this thing here goes to what? This whole fraction, the blue, tends toward 0, right? If p gets close to m, which makes sense because as we get close to the carrying capacity, don't we want dp dt to go small, right? We want the derivative to be very, very small. Likewise, when p gets close to 0, we want the derivative to be small as well, right? Because at the beginning, when the population is close to 0, we want there to be basically no growth, right? So I hope you're seeing why this differential equation does embody the two assumptions that we're trying to make with this model. Another way to write it would be this, if you like. And this is the way that I might like to see it, just for fun, I don't know. Just to, partially because m is a constant, just to be clear, right? So k over m together is a constant. Okay, any questions about how the setup is going to go? The next thing we're going to do is actually solve this, and it's a challenge. So you're gonna. I want to make sure like you're good on this first assumption. It's not quite as yesterday. It was like 60 seconds and you solved the exponential differential equation. It wasn't hard, but this is going to be a challenge to solve. It's definitely solvable. It's separable still. There's no t even in the equation, so we can definitely do this. And let me just say, if I'm going quickly here, I will make this set of slides available on Google Classroom tonight, and the video, of course, will be there. All right, so you ready to solve this? Here we go. Now, again, this is the kind of thing that once we solve it once, like, we don't maybe need to solve it again, ever. So I just want you to know that if you did forget the solution to the logistic differential equation, that you could rederive it with all the tools that you have. I'm not going to introduce any new tools here. It does get a little messy, though. If you separate variables, you get this, yes? Just say agree. Do you agree? I just divided both sides by the things that have a p involved, and I move the dt over, and now I'm going to integrate this. Yeah?
So, like the last one, does it matter if we don't know how to do this?
Yeah, like again, I think in the end, I want to show you how this is done, but this is so labor intensive that I don't know that you want to, when the time comes, especially like on the AP exam, like take the time to rederive this when it comes. That being said, I don't think they actually, well, we'll say more later, but the point is, no, we don't expect you to rederive this on the fly. But I do want to show you that it comes from all things we've done before. So that's like 1 over, keep in mind, I want to make sure you're clear on every stage here. There are a lot of letters here, but keep in mind that k and m are both constants, right? P is the variable we're integrating with respect to here, right? So using partial fractions, I'll just show you the work there. I can rewrite this way, right? Not knowing what a and b are, but then solving for them. I'm using the annihilator method here, yeah? Remember this? Okay. So that means that we can rewrite the left side in this way, apparently. You see what I'm doing here? It looks like a and b are both 1 over m. So I'm rewriting it this way, and feel free to check me on that. You can actually multiply this all out. That is a piece of algebra for you to check if you want. And when you do, you should get the thing we started with. But, of course, the advantage of the new form is that it can be integrated nicely. So, I've multiplied both sides by m. Are you okay with that, hopefully? Yes? Just because that makes things look simpler. And now I'm going to integrate. So we get natural log of p, absolute value of p, and natural log of absolute value of n minus p. And over on the right side, kt, and then a constant. Pause at any time where you need some more information. Combining using log properties on the left side, and then using, and you're not ready. I mean, you can see what we're trying to do here. Eventually, we want to solve for p, don't we? I mean, like, hopefully that goal is clear in our mind. In the end, we want, like, p of t. Is there a piece there? Where did this go? Wait, which thing? Where'd the 1 over m go? There's a 1 over m on both sides, and I canceled it. It's just a constant. Yeah, hopefully you see the goal in mind, right? Do we have the end in mind? We're trying to get p of t equals some equation, right? Like some function, p of t. There's still a long way to go here to solve that equation for p. But we are in algebra land now, right? There's no calculus to do here. This is just like solve that for p. Okay, let's do it. Well, the left side is p over m minus p. And we can raise both sides to e to that power of each side, right? And then we still need to isolate p, which takes a little bit of algebraic work. I'm going to decide to flip both sides just because I think we'll like that. Is that okay to do? Do you see what I did over here? I took the reciprocal of this side, and over here I took the reciprocal of this side, making both of those things negative. again, all algebra here. It's a little tricky. But now I can actually do this, which is cool, because now there's only one p in my life. Adding 1, dividing, multiplying both sides by p, and simultaneously dividing by this quantity gives that. Whew. Am I right that this is a little more labor intensive than the exponential? And then keep in mind that here we have, remember we have this old trick that if we have e to the negative c here, we can pull that out as one constant. Let's call it a, how about? So there it is finally in a box. This is p isolated. P as a function of t. Whew. So there it is in general, the solution to the logistic differential equation. Yeah, so you might just know that that's what it is. I don't know. Okay. No one will make you rewrite this on the fly. Does this also show forth the two asymptotic properties that I talked about earlier? Hopefully when you look at this, you see those two asymptotic properties too. As t tends toward negative infinity, can you plug negative infinity in for t, please? Tell me what you get. What do we approach? What does p approach? The whole value of this expression. When t is like negative a million, what do you get?
0.
Yeah, right, because this guy blows up, the whole denominator blows up, so the numerator is going to be fixed at m. We're going to get something that's arbitrarily close to 0. Now do it for infinity, too. Plug t equals infinity in. Not necessarily close to 1. What is this? This thing, if t is very large, then this term becomes negligible. Yes, this whole term. So what do we get close to? M, which is exactly what we wanted to have happen. So this, I'm just kind of doing a little reality check at every stage. Remember, we made those two conclusions from the differential equation, too, didn't we? Remember how we made those sets of conclusions from the differential equation as well. So I just wanted to see that that was happening here as well. So here it is in 2 boxes. There they are. There's the original differential equation we had, and here's its solution that we just derived. Now, a word of caution, your book does have it rendered slightly differently. And other people in other books and things like that may use different letters and different ways of showing it. In fact, the way I originally had it, where I had like Kp times the proportion of the carrying capacity that remains, sometimes people even write that way. But this is the way it appears in your book if you happen to look it up tonight or something. And just know that like they're thinking, and this is valid, K over M is a constant, so let's just call that K. But know that their K and your K are different, right? They're not the same. In fact, what is the relationship between these? So if you see like in one of the problems I think we're going to do soon, you see like they give you this differential equation. It says like 0.01 p times whatever, 500 minus p or something like that. Well then what, if you love this, if you love our way of doing it, then what would K have to be? If the carrying capacity is 500, and this thing they stuck out here, this thing is 0.01, how would you calculate our K value? If this is 0.01, yeah, you'd have to multiply to get this one, right? Which also explains why in the solution we have a little bit of, we also have m appearing here in the solution to their differential equation. All it is a change of constants, okay? So hopefully you're clear on that. I don't know that you'll need to know. I just wanted to like make you aware of that, because if you see this in your book, it'd be very easy to be like, oh, I see this and I used it. You might get messed up with the constants, so be careful. All right, so let's work this through together here a little bit. There's some grizzly bears. We got a graph there to look at. Maybe, I don't know. So it says, do I have all the information on there that's on here? P of 0 is 10. Yeah, okay, so that is recorded in the question. And P of 10 is 23. It's written a strange way, maybe. I guess this 10 years ago is, so we'll use that as our point of reference, is that point P0, we'll call that P of 0, maybe, I don't know. So on your paper you have that actually written out, I guess. And along with the differential equation for the solution. With constants, so we already know what m is, you can plug that in. You don't know what a or k are though, right? We have two constants to resolve. So let's use algebra to figure this out. This is not maybe calculus, this is kind of some algebra. Let's do P of 0 first. I think you'll like doing that one first, right? So apparently we get 10 if you plug in 0. So that's just 1 plus a. I think in a second you'll know what a is, right? Without having even used the second piece. Right? We haven't used P of 10 equals 23 yet. We will need that too. So what do you get for a? Great. And then we also have that 23 equals 100 over 1 plus 9 e to the negative k times n. So in a second you'll know what k is. Maybe 30 seconds. I don't know. Maybe not one. Take a minute to do that. I will see. Let me get my calculator. I'll do it together. And again, you may, I don't know, I haven't looked far enough into this problem. You may want to store the value of k, because I think it's not going to be a nice number like a was 9. Yeah, so I trust that, you can fill in the details here, but yeah, k is approximately 0.09889, etc. So maybe store that in k on your calculator or something like that. You might need it for a future problem, but for this question, I think we're done. We just need to write down the equation. P of t, I think that's what was asked, right? Find the population model. Okay, is 100 over 1 plus 9 e to the negative 0.09889. I don't know what he wants to do. T. Great. What are we supposed to ask next? Come again? I think there's supposed to be a 0 there, yeah. I think so. Okay. Use your model to predict when the bear population will reach 50, 75, and 100. Feel free to use your calculator's aid for that, right? Obviously, you can. In fact, you can even maybe just use graphical capabilities, right? Graph y equals 50, or 75, or 100, and see what you get. The only one there that seems problematic is, of course, well, I don't know. You think about it first. But you can solve it out. It's not that bad to solve algebraically either, I guess. You can do whatever you like, but somehow get an answer for this. Confirm that you get the same thing I do. And then, yeah, so 50 I'm getting about 22 years-ish. 75 I'm getting about 33 years. And 100 I'm getting, yeah, maybe never. I mean, like, practically speaking, there might actually be a time because, like, this is a discrete phenomenon. So you might actually say a certain year, but certainly the theoretical model predicts the answer never, I guess. But you could actually make an argument, I guess, that it does hit the carrying capacity and then just stay there or something. That's a deep philosophical question. Might be the first time you put the logistic equation into your calculator. It's kind of cool to see that, like, little S curve with two horizontal asymptotes. It's not a function that I think you studied a lot in your previous courses. You might have, like, mentioned it at the very beginning of pre-calculus just to show a pretty picture of it, but then never again or something. Right. What is the differential equation then? This is the next question, right? What is the equation for the rate of this logistic growth? I think this is written on your paper there. I've actually plugged in the things we know. K was 0.1. That's obviously very, very, very rounded. It's whatever we said, 0.09889. So what is an equation that gives the rate of change of the population? Well, there are maybe two answers to that question, right? Your first instinct, like if you were yourself a month ago, would have been just to say, okay, well, I guess that's asking me to take the derivative of the equation I have in my possession, the P of t function. And that would give you a derivative function. It's a little messy. It might require like the quotient rule and the chain rule and stuff like that to derive, which is fine. But this is also a derivative formula for this. It's just an interesting one because it uses P in this formula instead of T. Right? A lot of questions about the rate of change, like we even saw in the warm-up today on part B, can be answered just using the differential equation, right? So, for example, when does the rate of change start to decrease? First of all, does that question even make sense? Does the rate of change, what's going on with the rate of change over time? Well, it looks like it's kind of ramping up, but then it seems like there's a point at which the rate of change starts to go down, doesn't it? Keep in mind, P of t is a strictly increasing function, isn't it? It's always increasing. That is true. So the question here is not about the first derivative. We're talking here about the second derivative, right? And like back in the day, unit whatever that was, 4, whatever, when we were doing applications of the derivative, we did curve sketching and all that. We talked about like this idea of, point of inflection and all that. One way I always think of that is if you were like surfing the function, right? when would your hand start moving from moving counterclockwise to starting to turn clockwise? And you see that like right then, as you surf the function, it seems like maybe that's right in the middle of the wave is like when you start. Instead of doing this, you start doing this, right? Imagine the rotation of the surfboard. It's at that point of inflection. Where is the point of inflection? Let's see if we can figure it out. I'm going to try and use just this. I mean, I know one way to find the point of inflection would be take the second derivative of P of T using like two quotient rules and just terrible. And there'd be a product rule probably in there too along the way. It would be terrible. But let's see if we can get it just from using this differential equation. I'm going to take the second derivative, which for us right now is just taking this equation and taking one derivative. So I have d squared P over dt squared. Taking the derivative of this with respect to P is easy. It's just this, right? But we're not taking it with respect to P. We're taking it with respect to T, aren't we? Chain rule. Yeah? dp dt is always positive. We already talked about that, didn't we? So we just need to know when this is 0 in order to find the point of inflection. And for our particular example, that's at 50. And you could prove in general that the point of inflection always happens. Where do you think that the point of inflection always happens? Half of the carrying capacity, right? So the carrying capacity was 100. So this is not a general argument, but you could make it general by swapping in some letters, right? And you could show, using this argument, that the carrying capacity always happens at m over 2. Okay? And notice we didn't have to do too much heavy algebra here in order to do that. Though you could justify this using the second derivative of P of T. Actually, working it would be terrible. But yeah, sorry, there was a hand in the back. I mean, you good? Okay. So this is a little bit hard, and you have to really think hard about your chain rule and all that, like why I did why I wrote what I wrote here. But that is correct. And then if someone wanted to actually ask when that happens, that would be easy. We actually already did it. Didn't we say it's 22 days or something? Or 22 years, whatever we're talking about. Years, right, years. And just for fun, let's close by looking at the slope field for this guy. There's the slope field for this differential equation. And notice the solution curve just beautifully goes in there. Yeah?
What is like A?
Let's see. There are two. It's just a constant,
So
like K. But you will have to solve for it. It'll always be a constant. I'm trying to think if there's like a deeper meaning. Like, oh, it controls. It's like the aggressiveness of the bears or something. I don't know. I haven't thought about that. Maybe there is a meaning to it. I don't know. Notice, by the way, if you started in this park with a grizzly bear population here, and this was the DE, what would happen to the population? Where would the solution go if we? Yeah, it would also approach the carrying capacity, but from like above, right? What if you had a negative population? You can't, but let's just pretend.
Can you get more negative?
Yeah, it would become more negative or something. I don't know. That doesn't really make sense in the context of the problem. But the homework is homework 5 in the book.
How much money did you
Happy Valentine's Day, everyone. Math loves you.